Welcome to AI for Good, the leading action-oriented global and inclusive United Nations platform on AI. Organized by ITU in partnership with 40 UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end, as we will hold a 30-minute networking session in the neural network. Here you can meet, ask questions to our distinguished speakers, connect, and chat with the AI for Good community. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Great, thank you very much. So welcome everyone to AI for Good, AI for Climate Science. Today's session is with two fantastic speakers. So Gustau, Camps-Valls, and Manil, Maskey. Gustau is from University of Valencia and Manil is from NASA. The topic the title is A Collective Agenda for AI on the Earth Sciences, but it's really broader and focusing primarily also on observation. So we might not have given the observations enough attention yet in this series. And so today should definitely rectify this. So I'll kick off with Gustau and introduce the first speaker. So Gustau Camps-Valls is a physicist and he's a full professor of electrical engineering at the University of Valencia in Spain. He works on machine learning, remote sensing and signal processing. And he heads at the university the image signal processing group. It's quite a big group, 40 people now or so. So congratulations. I don't know how he manages. And they all work on the intersection of AI for Earth and climate sciences. But Gustau really early on recognized the big potential for machine learning in Earth observation. So I'm very much looking forward to his talk today. So I hand over straight to you, Gustau.
Well, let me just try to share screen.
Looks good.
That's good. Fantastic. So, okay. So, hi, everybody, and thanks for the kind presentation and the very nice invitation to this seminar series. It's really great to be here and to speak to such a diverse audience today. In this talk, I will try to introduce you like this AI collective agenda for the earth sciences. I want to try to convince you that machine learning or deep learning alone is not the solution to all our problems in the geosciences, and that we need like to take a step back and to think about the fundamental laws of physics governing the system, but also about the observations and also about the models that we are developing and the assumptions that we're making. And these are like the only way that I foresee to really have an advance and an impact in this very exciting field. Okay, so this is basically our little object of interest, right? The Earth. So we are asking ourselves questions like, what is the health status of the object? What are the vital signs? Can we monitor it? Can we predict its behavior, the future state? Can we actually do this in real time and ideally in an automatic manner? Well, in other words, what we want to do from a statistical point of view is to do inferences about the system. And for that, we use Earth observation data acquired by many platforms and sensor systems on the ground and many satellite sensors above our heads. With this help of, let's say, computers, statistics, and machine learning models, now we are able to estimate many different quantities, many essential climate variables from space, and like the ones here in this video. We can now estimate properties of the land, ocean, and atmosphere with unprecedented accuracy, and also study their evolution, either regionally or globally. We call these little objects data cubes, and they have, like, as you can see, 3 dimensions, space and time. But since we have to have like a holistic vision of the system Earth, we often want to do data fusion and aim to combine them all as much as possible. Well, this essentially helps us to tackle very urgent problems in the, to resolve and to tackle the Sustainable Development Goals, like, for instance, this one to derive explicit maps of crop health status, water stress, and also to estimate important variables of, let's say, gross primary productivity or estimating sun-induced fluorescent signals from space that give us some very valuable information for monitoring vegetation and forests, for example. But also, we are able now to estimate parameters of interest in the oceans and the coasts. So, for example, a whole science of the ocean is now devoted to estimate with machine learning and data acquired by satellites, chlorophyll content, suspended matter, ocean color, sea level rise, estimates, etc., right? Also, we have, in a similar way, developments in the atmospheric sciences that try to exploit many sensors to estimate air quality indicators like methane or CO2 concentrations, also cloud and aerosol properties, which are, of course, really relevant to monitor, and they have very, direct implications in both population health and also the climate. And for all this, machine learning has a certain impact nowadays, because essentially we are collecting tons of data and want to process them in an efficient and very efficient manner, right? But despite all these great advances, we are actually observing like three main challenges on the real and the direct application of machine learning or deep learning, in particular in the geosciences. Actually, these potent challenges go like this. So the first thing, and probably very annoying, is that the vast majority of deep learning models do not respect the most elementary laws of physics, like the mass or the energy conservation. Also, it has been argued that deep learning models just fit. I mean, they excel into that. There is no doubt about it. But nothing fundamental is learned in the end. Actually, these models are becoming so big and complicated, I mean, so over-parameterized that the interpretability of what these models have learned is often very compromised. And finally, I would like to emphasize that while these methods certainly capture some sense out of the data because they can approximate, they can classify, they can detect anomalies very well, how can we know that these methods actually capture something about the cause and the effects? Did these deep learning big networks learn anything at all? Are they interpretable? Can their decisions be explained? Can you robustly identify causes and effects from data with these architectures? Well, unfortunately, the answer to all these questions is no, but we are in the pathway. So machine learning and deep learning are exceptional, excellent interpolators, but do not understand the physical mechanisms, the fundamental laws, and the notion of cause and effect. My point here is that I think that we need to rethink the role of AI or deep learning, if you want, or machine learning in general, in the earth sciences. What is the role? And we want to do that in order to ensure kind of a real progress in these sciences. But for that, let me just take 3,000 years step back and think about the standard players in the scientific method, okay? So first, experiments that they typically lead to observations. Then, of course, system modeling, sometimes referred to as mechanistic modeling or process-based modeling, right? Which basically works with mathematical abstractions of the natural phenomena that you observe and then try to model it with typically parametric functions, parametric models. And the third leg, I would say, is, of course, the causal interpretation or the interpretability of the processes and the phenomena that you're observing. So we are always asking ourselves about the plausibility of these relationships in the natural world. All of them, they are, of course, interconnected. But now there is this orphan here. What happens with AI? What happens with deep learning? What is the relation of deep learning with all these definite, very good players in the science system? Well, of course, deep learning uses observational data to fit models, and this is currently done in many ways, in supervised learning, unsupervised learning, semi-supervised learning, all kinds of learning, multitask learning, and they also fuse heterogeneous information. And then, of course, there are deep learning architectures that can exploit the spatial temporal data structures, as we have seen before in the video. But deep learning alone is just one thing, and has to, in a way, should be able to learn representations that at least should be compatible with our previous physical modeling or understanding. And for that, you could just run your deep learning model alone and try to, cross fingers and hope that it actually resembles some fundamental law in physics. Or you could design algorithms that drink from these sources. So this is the field of hybrid modeling and has demonstrated, in particular, very nice advances in the recent years, trying to propose basically in 3 different lines of action in emulating the dynamical spatial temporal systems, also in parameterization of processes, because mainly of computational reasons, but not only. In this way, you can basically try to exploit or explicitly resolve processes that require high resolutions that you cannot cope with the standard system modeling. And the third leg, I would say that it is use this hybridization between, deep learning models and system models is essentially on the bias correction of the system models. These are like very nice opportunities in the end, and I think that they will play a more prominent role in the upcoming years. Well, deep learning should be also interpretable and get some sense or a notion of causality. Otherwise, what are these big monsters learning after all? Making these black boxes, let's say, grayer or more glassy, should definitely help not only in gaining confidence and trust in these machine decisions, but also would certainly make a decisive step, let's say, towards like the understanding through the data analysis process. So these are, of course, exciting developments in the fields, but we are not yet there. Real world experiments also play a role, and the interaction between deep learning and the experiments is really an interesting one. Essentially because you often want to test hypotheses that we generate with observations or from, let's say, theoretical reasoning. And optimal experimental design, this is a field, a very prominent field in statistics and machine learning, that attempts to design experiments that can best constrain the parameters of a model. And you can take this system model as a model and also the deep learning as a model. So what can we do in order to better improve our deep learning models or models in general? And actually, deep learning should not only answer questions about the what, but also about the why and the what if. Why not doing experiments with the models and in the models world? Are they robust enough? So are all these pressing questions that I think that this agenda could actually contribute into do. Well, this is more or less the AI agenda that I'm proposing here, where you can see that there are different aspects, different pieces that are joining together along the lines of the scientific endeavor. So hybrid modeling, combining system models, observations, and deep learning or machine learning in general, experimental design and causal inference, and both, let's say, modeling and testing, and they go hand in hand. So, in a way, you can be skeptical. Of course, I can bear with you. Deep learning is not learning any causal relationship. They just simply find the best associations or correlations between input and output. They learn patterns. And basically they minimize a cost function, but there are different linkages that one could exploit. For example, one could use causal theory to explain their functioning, let's say the feature relevance, but in causal terms, not just as an explanatory variance terms of the deep network. Or the other way would be like use the neural networks for causal hypothesis generation or learning causal representations. That could be an amazing venue to explore in the future. Well, actually, connecting experiments, you see on the top right, deep learning and system models can also help in answering very important questions, right? Like, for instance, which are the most informative experiments, or where should I sample better in space and time in order to constrain models? Or, for example, what are these parameters that I'm learning? Are they physically interpretable? Are these latent representations really causal or not? Okay, so with all that in mind, let me just go through these recent developments along these 3 different lines. There's this interaction or this interplay between physics and machine learning. The explainable AI, this is a new field that is capturing a lot of attention in order to, to explore or to explain what the algorithms have learned. And then last but not least, I will briefly speak about causal inference as well. Okay, so the field of physics-aware machine learning, sometimes it is referred as guided machine learning or informed or even science-guided machine learning, is really very emerging now. And here we just want to live in this interplay between machine learning and physics, and we want to exploit essentially all our domain knowledge to incorporate it in a meaningful way into the machine learning algorithm or pipeline. This prior knowledge can come in the form of equations or simulations or ancillary data in many different forms. In this simple taxonomy that we published in this survey paper, we basically summarize different approaches in which machine learning and physics can interact. We have basically algorithms that blend data and model simulations. We also have methods that can, let's say, approximate costly models like radiative transfer models in remote sensing with machine learning. We also have methods that can learn the multidimensional distributions of the states of the parameters of interest, and we also have methods that encode differential equations into the machine learning algorithm. Let me just give you some examples of each one of these approaches. In our field, we often face problems of classification and regression, like classifying or detecting changes in satellite images or estimating quantities or parameters for a particular pixel or region or parcel, right? So the first simple approach to incorporate physics and machine learning is related to this constraint optimization. So the idea here is to include an extra regularization term. And instead of looking for, let's say, fitting plus enforcing a smoothness or a sparsity through an L2 or L1 norm, we aim to minimize, let's say, the sum of all impossible solutions guided by a physical model. Well, in this toy example, in the figure, the authors wanted to estimate the different temperature of different layers in lakes. And they managed to incorporate this constraint basically with, trying to respect a known relationship between temperature and density as you go through the different layers in the lakes. Well, they minimize all these three terms: the cost, the smoothness, plus the consistency regularizer. And then they show that the method could behave more consistently and in some cases even more accurate, which was kind of puzzling because you were not actually expecting or enforcing to be more accurate, just more consistent. Well, this is a collective field known as hybrid model or hybrid modeling. And this field is about combining, let's say, ordinary or partial differential equations in machine learning. And it's becoming quite mature these days. But this philosophy is not new at all. Look at this paper 15 years ago, where a hybrid model was developed. Essentially, this was published in a chemical engineering journal. And the authors were interested in estimating a particular parameters, the speed of a particular chemical reaction, and then they combined two models. They combined a differential equation describing the dynamics, and then a neural network for the more uncertain part. The problem here was that, well, these type of approaches were kind of quite successful at that time, but they were ended buried in the literature essentially because you had to train the two models separately, and the coupling was not really easy. But now this has changed because of the popularization of differential programming approaches in deep learning. And we actually reviewed this in this paper. We reviewed the role and the challenges of deep learning and how the integration of deep learning with process understanding is, in our opinion, the way forward. Here on the left-hand side, you see a general framework to, let's say, physicize a deep learning model. So essentially, you incorporate like a last layer that incorporates some kind of consistency equation, like an ODE or PDE. And then on the right-hand side, I'm showing you a particular example, this deep learning model that can learn motion fields that are accurate, and also at the same time, they are physically consistent because they include an extra layer that warps the motion field estimates with a physical model. Well, the network weights are optimized end-to-end with this new differential programming language capabilities of deep learning. And actually, Marcus Reichstein presented a couple of examples more in his presentation two weeks ago. Of course, another exciting field nowadays is that of replacing costly models with machine learning. This is known as emulation or surrogate modeling, and this is there for decades already. But this is not only for the sake of a speed up, but also because if you replace a costly model with let's say a GP or a Gaussian process or a deep Gaussian process or a Bayesian probabilistic treatment, That will give you some extra advantages. For example, you will be able to propagate uncertainties, estimate uncertainties, and also the equations for the feature ranking comes in a closed form formula solution, which is very, very, very nice. On the right-hand side, I'm showing you here that it is basically very hard to differentiate the feature rankings extracted from let's say, the formal inversion of the model and the feature ranking derived from the machine learning algorithms. In this case, I think it was like a neural network, a kernel regression, and a random forest or something like that. So it is really hard to differentiate those rankings. So actually, these emulators encapsulated the physics pretty nicely, and of course, at a fraction of the time. So they are computationally very, very efficient. And last but not least, I think that this is really important. We are often facing this problem of forward and inverse modeling. Let me just focus here on the, let's say, on the down arrow, the retrieval algorithms. So we want to infer some parameters, but we are not only interested in estimating pointwise or retrieving pointwise estimates of the parameters of interest from, of course, simulations and observations, but we want to retrieve distributions as well. And this is very, very challenging. Well, in this particular work, what we did was basically learn these parameterization densities of an RTM. So we wanted to respect the RTM equations, the forward model equations. And then the problem is that, well, the model basically gives a Gaussian likelihood, and then we assume a Gaussian prior, and then we want to learn the prior parameters of the prior parameters that enter into the RTM. The problem is that doing the integrals, the integration with the RTM, which is a very complicated nonlinear model inside a Gaussian mean, is really tough though. But this can be, well, we managed to resolve it with variational inference. The good news here was that the convergence times were much faster and much shorter than the more traditional, or let's say exact Monte Carlo or ABC methods or approximations. And at the end of the day, you have like a posterior approximation with a predictive mean and a covariance matrix, and then you can derive like confidence intervals, but also like the full distribution of the parameters. Here, we apply it to derive prior distributions of several land parameters like canopy water content, chlorophyll, and dry matter. Yep. Okay, so far so good, but we can, well, at least we can develop machine learning models that can kind of incorporate some physical constraints, which is nice. But are these models interpretable? Are more interpretable because we are encoding physics? So this is an urgent question to answer these days. And we want to resort to explainable AI, which is a new field in machine learning that is picking up a lot of interest especially in the geosciences, because after all, we want to interrogate the model. And there are many different approaches. Well, not many. There are tons and tons of different approaches inside these families of explainable AI. And they can be characterized or categorized in different families. But I will just pay attention, for the sake of brevity, to sensitivity analysis. But in a particularly challenging problem, in the problem of trying to understand what an unsupervised algorithm is doing. In this case, we were interested in detecting droughts. And for that, we use spatial temporal covariates. You may imagine moisture, temperature, GPP, etc. And they were used as inputs to an autoencoder. And this autoencoder learns a latent representation that essentially can reconstruct well the data that you're providing. But we are not really interested in the reconstruction. We could, but what we did is to take into account this latent representation and try to come up with an anomaly score. For doing that, what we did is to add a Gaussianization flow. Remember that this latent representation is multivariate, so we wanted to Gaussianize that multivariate latent representation, and that is a good estimate of the log likelihood, and this is our anomaly score. Actually, the method performs quite nicely in detecting this Russian heat wave in 2010 that provoked a lot of crop losses and deaths, actually. But we are not only interested in the detection. I mean, it is very nice that you can detect this in an unsupervised manner, so without using any labels at all. But what we wanted to is essentially to pay attention to the explanatory power of this model. that it is not guided by any particular target problem. So here we applied this method called integrated gradients. And in integrated gradients, what is nice is that given this encoder, you can basically derive especially explicit maps in space and time of the most salient regions. So you can derive like feature rankings in time, and you can readily see that there are some particular combinations of variables that are impacting the drought detection for the algorithm at least. So it is interesting to see that, for example, a dry fall followed by a hot springtime may give you rise to this kind of severe droughts, and this kind of compound action of different drivers are actually very difficult to capture. And I think in explainable AI can give us some good news in the near future on this, trying to explain what the actual model has learned. Good. And yeah, you can read this. Understanding is more important and more challenging than fitting. And this is precisely my last point. Following from the previous talk by Jacob Runge and Ime Ufo, I just wanted to remember that the goal in causal inference is to jump from a mere ranking of relevance, let's say with a prescribed model structure, so X is cos and Y, to a more, let's say, sophisticated way of looking at the problem in which you derive a causal graph that describes the underlying mechanisms of the data generating process. So this is important for many different things to answer questions about, is this model simulation compatible with my data observations? Can I use causality to perform tests or testing hypotheses, or many other questions in earth and climate sciences, of course. Now there is a solid mathematical background and a lot of theories for causality from observational data and assumptions, but there are mainly four main families, and I will try to exemplify this in what follows. So the first, and let's say the foremost algorithm for assessing causality is Granger causality. Actually, it is more about predictability than causality. Here, you just want to check if using the past of X is actually useful for estimating the future Y or not. So basically, you run these two models with and without X, and then you just check for the variance of the residuals. Well, we recently generalized all Granger causality methods with kernel machines. And this is nice because this way you can cope with nonlinearities and also a very important caveat in Granger causality, which is non-stationarity or non-stationary processes. So we applied this to a very simple example in which we tried to assess the relationship between ENSO and soil moisture globally. And we noted that opposed to a simple correlation analysis, what we actually derive with this causal index is that much sharper identification of really predictive or causal or Granger causal effects here. So only, for example, the ones surrounded in green here, like the very dry areas in Sahel or the very wet tropical forest regions, are actually identified by the method as causals, and the rest are just spurious correlations. Well, a second, let's say, approach to work with time series and causality, it has to do with the state space reconstruction methods. Here, one essentially decides that X is causing Y or vice versa if you can recover the manifold structure of Y from the manifold structure of X. So this intuitively means that X has created some kind of information footprint in Y. And if you're able to identify it in this way and not the other way around, maybe there's some chances to identify that causal direction. The problem with this CCM algorithm is essentially that it is very sensitive to noise and also a strong coupling. And here we propose like a bootstrapping method along with another approach based on or combining information theoretical criteria that could alleviate these false detections in the model. Well, we could generate like causal impact maps here. In this case, very simple maps relating GPP, air temperature, and soil moisture. So essentially, you can confirm some well-known hypotheses, like in dry or let's say water-limited areas. GPP is mainly driven by soil moisture, and the temperature. Temperature is mainly an effect in the boreal regions, and soil moisture in boreal regions matches some kind of reduction in radiation and temperature. But there is a third family, I would say, of causal discovery methods. This third family is essentially going to the root, trying to check or trying to test the conditional independence between the different potential variables involved in the problem. So this way you can decide on the causal arrows. So essentially here you just develop two models to check the let's say independence of X and Y given Z. So you develop a model for Y depending on Z, another one for X depending on Z, and then you just check the residuals are uncorrelated or not by running a particular test statistic. Well, the problems of course, linearity and Gaussianity are there, and people have advocated or have proposed nonlinear versions of this particular method. And in the end, conditional independence test is the crucial thing here, no? And it is actually the basis for the famous PC algorithm. An extension of this algorithm called PCMCI, also by Jacob Runge, has been used to check differences in climate model simulations. So this way, you are not comparing model observations and climate simulations just in the spatial temporal domain, but you derive causal graphs from each one of the simulations and the observations, and then you can compare edges and connections between graphs, which in a way they are aiming to capture how much of the causal structure is actually encoded in the models and they resemble the observations or not. However, an important aspect of all this processing chain in causality in the earth sciences is as follows. Extracting causal graphs from spatial temporal data is very challenging because you have time lag correlations, because you have all kinds of what we know as teleconnection patterns. So for example, temperature anomalies in one region may influence precipitation in another region. And all of this is basically and typically divided in two main blocks. So first you extract some features of interest like running PCA, and then you apply your causal discovery algorithm. But these two processes are key and they are disconnected because PCA is essentially taking into account variance of the signal. It has nothing to do with causality. Well, in this last approach that I'm introducing here, we basically wanted to learn these teleconnection patterns by doing a nonlinear feature extraction that it is also Granger causal. And we do this with neural networks and actually with autoencoders too. So here we were interested in the connection between El Nino and global vegetation greenness, summarized here with NDVI. And here we essentially focus in Africa because it has been reported like the region most impacted by El Nino. I mean, the vegetation more impacted by El Nino. Here we are introducing this Granger autoencoder. Basically, again, tries to minimize the reconstruction error, but also we add another term in the loss function that tries to enforce that the latent space is also Granger causally related to El Nino. Okay, and then you can minimize everything, and then you can derive like causal impact maps like these ones only because you have access to these explainable AI techniques like integrated gradients as before. So it was very nice to see that there are some observed and clear reported patterns. In the top row, you have the Granger autoencoder. On the bottom row, you have the regular autoencoder. That it is not that clear in detecting the impacts. And well, looking at the literature, apparently the savannas and croplands were more affected, and in these particular regions of Africa, Sahara, also the Ethiopia and South Africa are mostly affected, and it was very nicely captured by the method. Okay, so as you may imagine, just a few words to finish my talk. You have seen that both physics-aware, explainable AI, and causality, they will need a lot of interaction between both computer scientists and domain knowledge experts. It is not just a question of downloading a software and run it. It is a question of asking ourselves, what is the physical law I have to respect? What are the reasonable and the surprising patterns? Is this causal or not? What are the hypotheses to preserve, etc.? So we need like a strong interdisciplinary action and education. And in Europe, we are taking this point very seriously. And we have articulated different networks of excellence and doctoral academies around the topics of AI and transdisciplinarity. An important mechanism here in Europe is ALICE, the European Laboratory for Learning and Intelligent Systems, coordinates research and interactions across members and institutions. And actually we have this research program called Machine Learning for Earth and Climate Sciences whose goals are really, really related to evolve AI in different ways. All the networks of excellence in AI in Europe have joined forces to create AIDA. And this is a new instrument to support excellent education and offers many advantages to students and researchers. So from here, I would like just to invite you to join in whatever form in ELIS and AIDA to, if you allow me the joke, to make AI great again in Europe. Okay, so just a final outlook. I hope I convince you with the story that machine learning and deep learning alone can do great things for earth sciences, but they have recently not answered many scientific questions so far. So we have posed these challenges in this perspective paper and also in this edited book, thanks to the contribution of leading experts in 23 beautiful chapters. I remember around the topics of consistency, interpretability, causality, but still, all these three topics are still in its infancy in the earth system sciences. And of course, we have many hurdles in the pathway. Domain knowledge is elusive. Interaction between computer scientists and physicists is always complicated. And education in this kind of synergistic environment is really complex and a hard task that will require a lot of efforts and, yeah, a lot of action on interdisciplinary education and curriculum too. So thank you very much for your attention.
Fantastic, Gustau. This was a fantastic talk and a great overview of many different areas. I almost made the scope far too narrow in my introduction. You covered a lot of different areas. As always in the series, we will now go to the second talk, and we will pick up questions together at the end after both of the talks. So it's my real pleasure to introduce the next speaker, and that's Manil Maskey from NASA. He's a senior research scientist at NASA and at the NASA Marshall Space Flight Center. He leads a team really looking at advanced concepts and AI, and he's also heavily involved in the central NASA artificial intelligence strategies. So in addition, he's also an affiliate faculty at the University of Alabama in Huntsville. So this, I think, will now be what I promised, more the focus on the Earth observations. And I just hand over straight to you. And I'm very much looking forward to your talk.
Yeah, thank you, Philip. And thank you, ITU, for the invitation. So my name is Manil Maskey, like Philip mentioned, and I work for the NASA's Earth Science Division mainly. But increasingly, the scope of the work that I do has been expanding to all of science, not just Earth science. So my talk is going to be a little bit different. I promise I won't show any equations. It will be more from the perspective of the data and data systems. So let's get started. So my goal today is twofold here. First is incorporating AI methods to better serve the science investigators and speed up the process of scientific discovery among those researchers. The second is enabling our data users to do AI and advance the field of earth science. And for that, I'll focus on specific topics of data, model development, and also building community around AI advancements. So a bit of a background. One of the NASA's strategic goals is to observe our planet Earth and do that very comprehensively to answer these societal issues and these research questions, right? And to do that, NASA develops and supports a large number of Earth observing missions. And you can see the scale of this, these from the NASA perspective in this visualization that shows the NASA fleet through 2023. So obviously a lot of data is being generated. The data collected by all these missions are managed by the Earth Science Data Systems program. This program also develops capabilities around the mission data, and it supports the large number of scientific user community by making the data openly available, which has been the policy for the last 25 years. In the right, you see the typical data lifecycle from mission to supporting the user community all the way to research and publication. So as part of the data systems evolution, to better serve our user community, we routinely look at these trends in science publications, right? So here's one we did in late 2019. We looked at last 11 years of AGU journal articles and their main topics. So what you see here is the top 10 keywords or topics for those last 11 years. As you see, last decade is dominated by climate-related topics, with remote sensing being close second. But however, you see in 2018, and I think this animation went too fast, but 2018 and 2019, machine learning and deep learning starting to emerge, right? And it has a strong hold on second or third spot. So that gives us some indication of where the community is heading in terms of science. This is just another view of last 2 years of the AGU publication. You see climate change and machine learning side by side. That gives you another indication. So we extended that same study across other major journals and did a little bit of deep dive. So here you see 4 major journal publishers in terms of earth science research. The study showed us that the use of especially the supervised machine learning techniques in earth science has increased significantly in the last decade. So this chart goes a little bit deeper into individual journals. This gives a view of use of supervised machine learning in each of the subdomains within earth science. As you can see, the biogeosciences and land surface research, they probably lead the area in terms of use of supervised machine learning. So we wanted to explore what kind of data is being used by these supervised learning, just to give an indication from the data science perspective. So it's surprising to see that satellite data is not the topmost data being used within the earth science. It's the in situ data and the model data. And our inclination there is that those data are readily usable within the framework of machine learning. Open source tools and things like that, that's already out there, right? So there are some data that are heavily underutilized in terms of our perspective. So we then polled our NASA science community and asked them about the data related question with respect to AI. The questions focus around the source data, the type of repositories, type of data, training data generation approaches, and what are the efforts required, reusability of these training data sets, and also a catalog for sharing and discovering these. So it turns out that the researchers' AI research and application most use data from the science data repository that we manage. And those come in form of scientific data products. The highlighted response here are of interest from the data science perspective. For example, 61% of the respondents mentioned that they create their own training data sets, even though there's a research overlap between what's already out there, right? So these are the things that data systems is concerned about and in the process of improving that for the user community. So the takeaways from these studies are that AI/ML approaches is rapidly growing within the earth science. That's not a news. There's a lack of training data sets. There's a need for open sharing of training data sets. I'm just talking from the supervised learning perspective here. And there are certain types of data that are heavily underutilized, right? And we also noticed that from the analysis of the trend and the survey, that the AI projects are mostly presented as research results. Not many of them have taken that and put it into production type of environment where you get tested against the real data. So from our perspective, data systems and AI go hand in hand. As an adopter of AI, data systems is using AI to improve efficiency of data systems operation and providing like seamless access to data and information discovery, while we also have to keep the open data policy, right? So what that means from the data systems management is that data, in every step of this data lifecycle, there is an opportunity to infuse these AI/ML approaches to better serve our user community. But and to the right here, you see is we also fully realize that the practical steps need to be taken to broaden the advancement of AI within earth science, right? And for that, we're relying on these open science principles, which includes the community building part, open platforms for easy access to AI services, building these benchmark training data sets, and also certain research to production transition for ones that have really matured in terms of AI results. So what we have realized is that cloud computing plays an important role in this relationship between data systems and AI. But before I get into some practical examples here, I want to give you some context in terms of NASA Earth Science. NASA Earth Science is migrating all of its operations, or most of its operations, to cloud computing environment. And that's mainly to address the challenges from these large data volume missions that have presented the challenges of data archival and the processing needs, which is just not possible in the on-premise system. But that also opens up an opportunity for AI for Earth science, right? So because the foundational elements of that have shaped AI are this data, computing platforms, and algorithms, right? So if we already have the data. The cloud platform helps us shape some of these AI needs, and which can also foster development of these advanced algorithms. And these cloud delivery models, each of these, like shown here, support certain aspects of AI. So I just wanted to mention that cloud computing and AI is helping us drive some of these advancements. So let's look at using AI for knowledge discovery. Specifically, we want our users to maximize the data that these expensive missions have generated, right? We have lots of data, but how we can leverage that for AI. So this is an interesting result of knowledge discovery within earth science. Here, scientists use AI to map crown size of each tree over a land that spans 1.3 million square kilometer in West Africa, Sahara and Sahel and subhumid zone, using sub-meter resolution satellite imagery. So using this approach, the researchers were able to detect over 1.8 billion trees. So this was an interesting discovery because although the overall canopy cover is very low in this dry region, the relative high density of the isolated trees is very surprising, right? So the assessment mentioned in this paper suggests a way to monitor trees outside of forests globally and to explore their role in mitigating degradation, climate change, and so on, right? Carbon intake. The key here is that these types of knowledge extraction is probably not possible without purely data-driven methods like that AI supports on large-scale, large archive of data. And from data systems perspective, AI provides us the means to maximize the use of these large archive, and this is one of those examples. So to further explain why we are doing this, let me show you an example of a typical data exploration. Let's say you wanted to study fires, right? So fire smoke is fire has a lot of consequences for atmosphere, right? It infuses these harmful pollutants. The smoke air can travel downward to several kilometers away, right? So if somebody wanted to study fire events or respond to a fire, a NASA user will typically go to a visualization tool like shown here. This one is called NASA Worldview, a fairly popular tool. And you can go there and turn on a layer for fire. So you'll see the smoke, right? Then you can turn on maybe a thermal layer and you notice where exactly the fire is. And then you will go look for that particular location, get the data, download the data, and you'll do analysis. So alternatively, what if you could let machine learning do the identification of these smoke or fire across your archive, right? So here's a animation that shows one such detection in 2019, I believe, in California fire. So the idea here is that you can let the machine learning go and learn from the archive all these instances of these events, and then you can then the data exploration becomes much easier, right? So the last example was a bit easier because the NASA tool, Worldview tool, already had a thermal layer, and that could be easily used to detect these hotspots. But what if we have an event like high latitude dust? These are not very common, so it's very difficult to pre-generate and archive these in a tool like Worldview, right? But machine learning can do this. Another example is this transverse cirrus bands. I'm just showing you a few examples here. These are very common cloud patterns that causes turbulence, so it's very important for air traffic. Again, you can do the same thing. Let it detect all of these across the archive, then you can tag them and put it in the database or archive, right? So once you have these automated detection of events, to speed up the scientific discovery process, you can build a portal like this, right, where all of these are pre-detected across the archive, and then you can do climatological analysis like you can see here, like figure out a time frame and see its spatiotemporal pattern. It not only allows you to look at climatological aspects, but also looks at particular use cases. Let's say you are interested in smoke in this lake region, right? So you can go into that. It's especially useful for early career scientists who basically start their career by studying certain types of events, right? So this gives them an easy way to get to the data quickly and do their analysis. And this is all powered through AI. So the next area of work related to search and discovery is to speed up science is the notion of search by example, a case where user is interested in searching across the archive for similar looking images. So just like Google search, right? You give an image and it returns all the similar looking image. The idea here is facilitating this search across archive, and the information is encoded in an image, right? So here's a schematic of how we are tackling this problem. The basis for this approach is the self-supervised learning approach. So the earlier examples of event detection, those needed training data sets, right, for smoke and transverse cirrus bands, specifically training data sets that the machine learning models can learn from. So this approach is on the other hand, generates features from the image, which are these vector information called embeddings. The idea is that an image and transformations of that image, same image, should have the same feature representation. So when we create these embeddings across the archive and store them in an indexing system, then you can send a query image, and the embeddings for the query images can be generated, and you can use some sort of neighborhood search algorithm to find the best matching images. So we are still in a prototype phase of this, but this animation will show you where we are going, right? So user will come to this map type of interface, select a region, and they said, I want to look at 5 images that looks like this sample images, and it returns, right? So we're scaling this across petabytes and petabytes of data. So the last search topics I showed were to leverage the AI for search and discovery to support growing number of users, right? So, but we also have traditional users who will search through our data, which is going to be in the scale of 250 petabytes in a few years, who just want to do the data search in traditional way, which is putting a keyword, right, and searching across the catalog and so on. So earlier I talked about looking at publications for trends, but those publications also capture the domain information. that can be utilized by AI for enhancing these core services that include this textual information to describe data, right? So specifically, I'm talking about natural language processing on a scientific knowledge base derived from this corpus of scientific literature. So here is a practical example. NASA Earth Science uses a catalog called Common Metadata Repository, or CMR for short, to describe its metadata records. So CMR leverages a control vocabulary of science keywords to help ensure Earth science data are described in this consistent and comprehensive manner, right? These are manually assigned currently science keywords. So it's possible that there are inconsistency in terms of the expertise level of these curators, that you can find inconsistency in this assignment of the science keywords, right? So if you assign wrong science keywords or inconsistent, then it can propagate through the data search, and the search results become inconsistent. So the question is, can we augment this process of keyword assignment? So the key concept that we utilize here is called the word-to-vec. Very simple. Word-to-vec is a neural network approach used to construct vector representation of word, and which is called the word embeddings, compared to the embeddings that I talked about from images earlier. So what it does is it breaks down the words into these latent variables, each of them capturing a hidden relationship that exists within the corpus, right? So we developed a specific word embeddings for Earth science based on the literature that we had access to. It's about 88,000 documents and so on. So then we created this classification system where if an abstract is submitted, the word-to-vec will take that and generate these science keywords, right? So this is one tool that we have already moved through the production environment, and it do something like that when you give this system an abstract of a data set, then it suggests to the curator, hey, these are the possible science keywords that you should use. And if there are error, they can also let the system know, and it learns from that as we move on. So next, I want to address the problem of difficulty in transitioning these AI models from research to production. In practice, we always talk about this research results, right, which are published in these prestigious journals, but we don't very often talk about the practical side of the things, right, the application side of the things, and applying those methodologies from these prestigious journal papers, research papers, to solve real-world problems. Because to solve real-world problems, you need data, you need good data, you need to organize that data, label that data, and you also need to select parameters of that data that can reveal the answers for those very hard questions, right? And this is a difficult process. So this next example application of using AI-based hurricane intensity estimation system, I'll try to demonstrate the nuances of deploying a model, research model, into production. So I will skip the model development part, but our team here developed a deep learning-based approach to estimate wind speed of a hurricane given a satellite image, right? Mainly to address two issues here. There seemed to be inconsistent estimation in current approach, which where different experts' estimation differ by substantial amount, and generally the estimation could not be performed at the same rate as the data is being collected, right? So luckily, this problem is very ideal for AI because we have good data. We have hurricane wind speed estimation for almost a century now, right? And we have satellite imagery for at least 2-3 decades that we can co-locate with that hurricane wind speed information and create this good set of training data sets. We don't have to label on our own. So this is ideal case for using AI, supervised learning-based AI, right? So we're able to develop this model, whose result I'm showing here for one hurricane case, Hurricane Earl. As you can see, the gray dots, which aligns fairly well with the observation, which is the red line. So we reached, I think, about 11 to 12 knots root mean square error, which was much better than what was on the literature. So we were able to publish a paper, and our research was done, right? So a typical machine learning project follows this life cycle, where the solution addresses a problem in that domain. You acquire the data, clean the data, make it ready for algorithms, then develop the model, train the model, refine the model, and that's an iterative process. You get to a reasonable solution and you publish a paper. But people usually don't go that extra mile, right? Researchers, because their probably research ends. Now, can we go that extra mile and put this model into production? But it's a very difficult task. Before you do that, we need to ask a few major questions, right? How do we ensure the confidence in this model over time? Meaning that the incoming data will change as we apply the model over time, which means that we'll need to retrain again and subsequently redeploy the model. So there's a lot of nuances here. So these are the additional steps that I'm showing here to the earlier life cycle. And this is an iterative process, right? There are model outputs, which are basically numbers. How would you present that in a practical settings, right? So you need to interpret that model, put it in an intuitive way, and people can look at it and make judgment about its value. So this is drilling down a little bit more on the deployment side of the things, and I'm not going to go into detail here, but there are all these issues that you need to consider before you deploy into production. So with those considerations, we built an event-based workflow where once an outlook of a tropical storm or hurricane is posted, the system starts collecting the data regularly, right, every 5 minutes, and start the estimation process. It interprets the estimation and puts it into a situational awareness tool like this. Here's a demonstration of some of the archived hurricanes, because there's not a hurricane right now, active right now. And it tells users what they're seeing, right? How is it making the prediction? Looking at that particular image, what is the observation value, and so on. So obviously, the hurricane model that we developed did not work very well in production when we first deployed it. We used the new data. I think it was hurricane season 2020. We let it run for a full year. The results weren't that good. So we used that data from 2020 for the entire hurricane season and retrained the model. So we approached this both from the data side and the model side, right? So we were able to infuse new data, retrain the model. For the model side of the things, we wanted to involve community to enhance the existing benchmark, right? The expertise are there in the community as well. So before I go there, I wanted to mention that we were collecting these training data sets for a lot of different phenomena, not just hurricane wind speed, right? So there's a benchmark, there's a way to do this benchmark, training data set, quickly benchmark them, and we needed a solution to reshare and catalog these, right? For that, we partnered with the Radiant Earth Foundation, who are developing these standardized cataloging solutions. So we can point to our users to, hey, these are the training data sets. We don't have to recreate these, or we can just build on top of this, right? So one of the ways we are involving community in our data system approach is by running these data science competitions. So we all know, right, creations of these benchmark data sets, such as the ImageNet, and the subsequent challenges that competitions drove these early AI successes in computer vision world. So the same approach we're following here. Once you have a high quality data sets and initial baselines, these competitions can be leveraged. The key here is to have a very focused problem and constrained by these labeled training data sets. So we ran a hurricane intensity estimations system from the earlier application I was mentioning, and we had a big turnout, right? And the results were amazing. So as far as the first three winners I'm showing here to the left, they included some of the considerations that we never thought of in-house, right? So, and they improved the accuracy by almost 50%. And this is some of the detail in terms of improvement they made for individual hurricanes here. In most cases, it's performed far better. So this is another example of flood extent detection, which we ran the same type of data science competitions. I'm not going to go into detail here in the interest of time, but it's the same approach here. Flood is another type of event that causes damage, right? It's relevant to disaster response, right? And it's a little bit of challenging because detecting flood extent requires some in situ observation, right? You need to go there, right? So if AI can help that by doing this damage assessment or mapping the flood extent, then we have a lot of value in addressing this challenge, right? The problem here is that we need high quality training data sets and large amount of training data sets because flood is very difficult to map because it has water, and any water looks like a flood damage. And so to tackle this problem, we actually involved experts in the Earth atmospheric science domain and earth science domain. And we involved students here, right? We had students work with the domain scientists and create the training sessions and rigorous validation. The approach we took was we developed this labeling tool that integrated with the archive directly. Right? What that allows you to do is do a collaborative labeling of these training data sets. So I'm just showing you some example of how one goes by creating these training data sets. For this particular case of flood data sets, this is some numbers here. We particularly used synthetic aperture radar data set because of the cloud being a factor during the rainy seasons or rain, which causes mostly the flood events. Another aspect to look at it here is that the training data set, which is generated for different geographic areas to model these diverse flooding situations, right? So once you have these training data sets, we created a baseline. I'm not going to go into detail here of the approaches here, but two approaches were created. We had a very good initial baseline. These are some of the results of the baseline. And the idea here is to, again, right, can we run a data science competition and have these open solutions to these outstanding problems, and can the community do better on these, right? Again, we had a good turnout, good results, accuracy about 77% IOU. So that is from the community side of the things, right? So when you put all these data system components together, which include AI-assisted core services and also the user-centric AI services, that is, you can put this together in this notional architecture, which we are envisioning. So this is enabled by cloud computing, obviously, and that provides a framework for rapid algorithm development, benchmarking with co-located data in the cloud, iterative deployment of AI models, and also facilitates enhancements of this core services that we can provide to our users. So in summary, data, I talked a lot about data, right? Creating these training data sets. Data is the key differentiator here, right? Models, they're now freely, openly available. Most of the cases, these are open source tools that you can pick and choose these model architectures. But having that curated large scale training data set, that seemed to be the differentiator in most cases. Obviously, we need AI approaches that can operate as part of the core large data system, that type of data system that we're managing. And cloud computing can obviously shape some of these approaches. Also, before AI can be widely used in critical enterprise data systems, we need new set of robust pipelines to manage the full AI lifecycle, which means the process of data collection, preparation, model development, test, and evaluation, and integration of models into a deployed system without perturbing the operational systems. And also the flexible architecture that allows software systems and AI algorithms that also considers evolution of these emerging trends, right? There's always advancements in AI algorithms, and you need to be able to take that, including the community input, and put that into a pipeline, deployment pipeline that can easily be evaluated over time with new data, new models. That was my last slide. Thank you. And here are some resources that you may find useful from this talk.
Fantastic, Manil. Thank you very much for a really good talk. Before I hand over to Duncan for questions, just if you, like me, went on the neural network platform, clicked on audience, you wouldn't maybe find your way back to the chat because you have to click a button called video wall. And on the video wall, you can then post your questions. So feel free to click that button and post your questions in the chat at any time. But you already have some questions. I'll hand over to Duncan.
Absolutely. No, thank you very much, both of you. It was a really interesting dive into both the research and then the kind of operational aspects of deploying these models. There were a couple of questions asking about having access to the slides, but I think that's okay. I think Manil has already made those available, and those should be up on the website hopefully in the next day or so. I think briefly, so the first question on my list anyway is to Manil, and is about the statistics that you shared right at the introduction of your talk. Do you have a citation for those? Are they available in publication yet, or
yes? Yeah, I can share that. It's in multiple publications, so I'll share that.
Okay. Yeah, no, I think that caught people's attention, so it'd be great to maybe pop it in the chat when you get a chance also.
Yep.
Okay, and sorry, let me find more interesting questions. So there's a question for Gustau actually. So you gave a nice kind of overview of some of the other causal approaches that that maybe Jakob didn't have a chance to chat on last week. Michael Spicer points out that well, it seems to him that there's a lack of kind of MOOCs and online courses in causal modeling, especially with concrete examples and coding exercises, and yeah, building such a course would greatly contribute. I guess it's no small order, but is that something that is, you know, happening, or?
Yeah, I think that he's she, I cannot remember the name, but I think he's right. I mean, there's not like a lot of MOOCs on causal modeling, but it is also true that the causal discovery is not really well covered. But and it is the modeling is basically you have to search for literature and epidemiology and econometrics, and not especially neurosciences. But for a modern take, I would say that in causal inference and discovery, I think I remember there is a course in Coursera, I think, by a professor in the Pennsylvania University. I think there's also like a very nice initiative in Bayesian statistics and causality. Maybe I can search for the link. It is on Criteo, I think. This company, they are like a good material there. And other than that, I think that you should follow Jonas Peters. He has fantastic lectures and great videos, and the book, I think it is for free. And yeah, I think it is yeah, a lot of material out there. Yeah, I will try to post some links. And
there's slightly more kind of philosophical follow-up question from Michael actually. How do you think about the question of what are the variables? So I think
what are the variables?
So formulating the scientific problem can be half the battle. So in kind of, I guess with reference to causal discovery, right? You know, how do you narrow down your choice of variables such that it's a manageable question?
Well, the point is that in causal inference and in discovery, you have like a bunch of assumptions. So most prominently there's causal sufficiency and the causal faithfulness. And in the causal sufficiency is essentially, sounds like very similar to assumptions about the completeness of the causal graph. So you have to assume that you have access to all the possible variables influencing the others, right? Of course, in real practice, this is impossible or very impossible. This assumption of causal sufficiency is actually equivalent to the assumption of independence with respect to an exogenous variable. But anyway, answering the question, of course, I mean, one could try to derive a causal graph from whatever you have, and then just pay attention to the parents of your target variable. If you're interested in a particular variable of interest, then you take a look at the causal parents, and those will explain the problem for you, and you don't have to consider all of the other variables influencing the parents of your target variable. In a way, it's like performing a causal feature selection. So definitely, it's a way to go. Yeah.
So that has a role in kind of dimensionality reduction as well.
Yes, exactly. Yep.
Yeah. Brilliant. Thank you. Manil, is it question on a bit more detail if you have it to hand or available on the AI tool and the example you showed for smoke detection? That caught my eye too. Was that supervised or that was fully unsupervised?
That's supervised.
It was supervised.
Yeah.
And just a kind of straight CNN segmentation model, or?
Yeah, it's a pixel level CNN model. Yes.
Yeah. Okay.
Yeah, I can share the publication.
Have a publication or something.
I do. Yeah. I'll put together a list of publications that's relevant to this. Yeah.
Yeah. No, that's great. I mean, so I've been working on some similar or segmentation or detection tasks, and this kind of query search that you showed off, where you just you find a little image of something and you say, go and find me more of these, resonated with me. Is that how close to being operational is that? I mean, can I just say find me a cloud that looks like this and it'll really work, or is there still I know? Yeah,
so the operational will be at around September of this year.
Okay.
Obviously, we have this is designed to be for only RGB right now, right? So
that was going to be my follow-up question. Yeah.
So any data products that we have that are generating the RGB imagery will work on that first. If you want to play around with the prototype system, I can certainly send you the link too. It will mostly be around MODIS archive for now, the prototype.
Great. There was also a question for you, Manil, or a comment in a question from Bastian. I think there's great efforts to make this NASA data archive so useful now and valuable. And one question here was, do you integrate expert feedback into this if people find issues with it, and do you put that in? And I have another follow-up question, which you can take separately. Is these are technically fantastic changes, going cloud-based, putting the compute with it, everything. But how do you plan to make this open in a sense that the wider community, I'm thinking particular people in the developing world, have access to some of these fantastic resources that they find hard to access at the moment?
Yeah, the key here is that sort of is the opportunity created by cloud, right? So the idea there with that similarity search approach is so that people don't have to download the data, right? Unnecessary data. Most of the time, science is all about learning about this phenomena that only occurs very sporadically, right? So if you can present that in this form ahead of time to users, they don't have to download the data, which costs if your data is in the cloud, right? That's the egress problem. So if you can present these phenomena ahead of time in this interface, which are powered by AI, then they only download, or not even download, the data that these are already detected, right? So if they want to further study that, they only download a subset of the data, so the cost is minimized. And to be ideally, you want people to come to the cloud so that there's processing is already next to those data that are relevant to them, right? So in that sense, it's actually accelerating access to meaningful data for people who don't have a lot of storage and computation capacity.
I think I mean, even for us, we're not short of resources in Oxford, and to be able to access these big data sets, kind of where the compute is hugely valuable. How much progress, kind of concretely, are you making with some of the archives? And these are huge archives. I mean, Modis alone, right, is a few petabytes. Is most of that available now on the cloud, or is it kind of progressing by year or by product?
Yeah, the cloud migration is a bit slow. Obviously, there are a lot of nuances in terms of security and all that comes with going to the open cloud. But most of the high value data sets, including Modis, should be moving to the cloud by end of this. A lot of these reanalysis model data are already in the cloud, like Amera.
Yeah.
And
a lot of the Modis too. Like, the Modis ones I found don't have the clouds into them. They're kind of like the surface properties and stuff.
Okay.
I like the clouds, but Gustau, I wanted to kind of dig a little bit into one of the projects that you showed off. So you had this nice variational inference approach that you talked about. Is that, so you mentioned that it kind of struggled a bit with multimodal posterior distributions. Is there some way of combining that? I've been trying to think about how to use normalizing flows in this context. Is there room potentially for something like that?
Myself. Well, yeah, the biggest problem is in the multimodality of the posterior approximations. Yeah, in a way, it is a very, very challenging problem. I mean, from the point of view of tractability, and variational inference can help, but it is not the panacea here. Yeah, well, at the end of the day, you are forcing one forward pass with the RTM, which can be potentially very, very costly, and then let's say the decoder, it is very sensitive to the noise that you're putting in, because in the encoder you are trusting your model, so you don't want to put too much noise in there for obvious reasons. But then when you're decoding for the, let's say, for the parameter estimation, that's the problem is coupled, and it is really hard to disentangle. No? There are ways to resort this problem, let's say, but typically it's regularization or just encoding like very ad hoc rules. Okay, so like just sample in this region, sample in that region for that parameter, but it is really not what you are aiming for, right? You want something that it is automatic and learns that from the data, no? Not forcing like ad hoc thresholds or things like that. But still, I mean, it is a possibility, but it is really hard. It is really a very, very hard problem, because most of the times the data that do not like correspond to the statistics that you are expecting from the simulations, so they do not match, and then they are irreconcilable in a way, no?
And you don't know the uncertainties always. You don't know the I know that problem. Okay. I mean, there are approaches. I forget with the group now in Germany, but they've been doing kind of neural likelihood estimation. I mean, presumably you could do variational inference over the likelihood, which might be.
Yeah, I'm not really sure about that approach. What we have been exploring is the field of normalizing flows and the invertible neural networks.
Yeah. Okay.
Which is kind of a nice approach, even though that, again, it is very difficult to domesticate monster. So there are like very critical parameters to tune, and but it is a very nice idea that you solve the forward and inverse model in just one shot, in just one model, right? Because it is invertible, so it is easier to go in the forward pass because you have like more knowledge about the model, and for the same price you get the inverse, ideally. Okay, again.
I just talked about you offline. Very interesting. Good. Okay. Philip, did you have any other questions?
No, I think this is probably a really good time. We're exactly on time. It's a good time probably to wrap us up. And thank the speakers again. This was a really, really good session. I hope we can share the slides. There were lots of interesting references, and I think people asked already desperately for them. Maybe a quick word or two quick words before we go. First of all, in terms of the future of the series here, we will continue. There's no talks at the moment advertised, but we've decided to slow down the pace a little bit. We've had a very rapid pace over the last month, and this was good, but it's also hard for everyone to make it every week. And so stay alert. There will be more talks coming, but they will be probably at a slightly slower pace, maybe once per month or so. But we will continue. That's one thing. The other bit is with a neural network, there's now a networking in the platform. I haven't done it myself yet either because it's brand new, but I think we can just chat in the neural network, and I think the speakers might be available too for more questions. So don't run away right away, and I hope to see some of you there. But let's thank again both Gustau and Manil. It was a really, really great session.
Absolutely. Thank you both.
Thank you.
We're handing back to.
Thank you, Mark.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the satisfaction survey, connect with interesting profiles, or speak one-on-one using the chat and video function. After the 30-minute networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits and poster boards, and build your personalized AI for Good program. It was a pleasure learning with you today. See you at the next AI for Good.